Good morning, everyone. Welcome to the EasyPower Tuesday Refresher. My name is Jim Chastain. We've labeled this presentation Beginner's Corner, and in the time provided, we expect to focus on how to utilize the EasyPower tools to conduct an arc flash study. Now, if you really are new to the subject of arc flash, I invite you to stay tuned because at the end of the presentation, I will be announcing a free series of presentations which go far deeper into the larger topic of arc flash compliance and how to save money in the process of achieving compliance at your facility. So please look for that. So NFPA 70E is a document that's referred to pretty much by all as the industry standard guide for an electrically safe workplace. And the golden rule, according to NFPA 70E, is the only safe electrical circuit is a de-energized circuit which has been tested and grounded if possible. Well, there are times when work must be performed on live exposed electrical circuits, and NFPA 70E describes the procedures for safely working and the conditions which permits that. It's also the document that's referred to or used by OSHA to judge compliance when a company has a problem. And so that's what we're going to be referring to as we get into a discussion of arc flash. Now, one of the things we'd like to do during these presentations is conduct a poll and get some feedback from the audience. This morning, I'd like some response, if you would please, to a couple of questions. And so here's the first poll question. Where do you currently stand with respect to NFPA 70E? And here's what the responses were. And then the next question, the next poll question, what areas are offering you the greatest challenge in terms of the arc flash compliance? Each quarter we conduct a 4-part series on arc flash compliance, and this quarter that will be held in October, and each of the 4 presentations are free and go directly to the basis for all of NFPA 70E compliance. So appreciate the feedback. Here's where folks stand on this question. And again, not unexpected, but it does help me understand kind of where the audience stands on the topic of arc flash. So let's go to some references I'd like to share. From the control box on this webinar, you can download one of the 3 handouts I've posted. These are also available on the EasyPower website under Arc Flash Resources. First and foremost is Practical Solutions to the Arc Flash Calculations. That's a very well received document on how to conduct an arc flash study. There's a 10-step approach to arc flash compliance, which is more of a common sense approach to what the trade-offs are in any particular case. And then very frequently, more and more, the topic of calculating incident energy for low voltage comes to the surface, and that application note's available. And then finally, I'd like to recommend for anyone in this position to have your own copy of NFPA 70E. There's a new edition that's due out within the next 6 weeks. And so I encourage you to subscribe to that or buy a copy. It can be purchased from the NFPA website. And again, this will be, the document's updated every 3 years, and 2018 is the new date of the new edition. So look for that. Okay, the point I want to make is compliance is more than just a study. And that's one of the things you'll find when you get into the details of NFPA 70E. It requires a complete safety plan, and that's a document that defines the responsibilities for your company. Frequently, the arc flash safety plan is just part of the overall corporate safety plan, and very frequently falls into the category of electrical safety. There's also a discussion in there in NFPA 70E how you calculate the incident energy, how you determine the correct PPE, the training that's required, the appropriate tools that need to be utilized, and then ultimately the labels and the boundary and making sure personnel are aware of all of that. Well, to start with, for this discussion and for anybody dealing with arc flash, probably the most accepted common definition of arc flash is the inadvertent flow of current through the air gap between conductors, which is accompanied by a rapid release in energy and heat. And that unit of measure, that product of that calculation, is referred to as incident energy, and the unit of measure is calories per square centimeter. Now, with that definition, you might be surprised to hear that it's counterintuitive to claim that higher currents don't always mean higher incident energy. I refer to this as the arc flash paradox. Other people refer to it as a short circuit paradox, but I think it is significant enough that, especially for a beginner, to grasp and have an understanding of what's behind this is an important point. So let me jump into that. And as I do this, I'm going to jump into EasyPower and basically show and describe this particular paradox. So this is the EasyPower tool suite. What we're going to do is start a new one-line diagram. To do that, I use the tool palette here on the left vertical sidebar. And this is actually an example of a real conversation I had with a tool user not long after I started with EasyPower. He said he had the responsibility of labeling all the above ground electrical distribution systems in an oil field. He was in Oklahoma. He said, "Jim, I have a problem with your tools." I said, "What do you mean?" He says, "Well, here." So we were on a call very much like this, and as he described his system, he had me build a one-line diagram. So we take the utility icon and we connect the two-winding transformer, which in this case was the utility transformer. And he said, put a bus on the secondary side of the transformer. Now you notice as I do this, the tool recognizes that there's a need for an assignment of voltage. His incoming utility was at 12.8 kV. He said his distribution system was at 480 volts. So I type in 0.48. He said, all right, extend this bus out. As I move the cursor around the screen, you'll notice it takes on a different cursor icon. Here we're showing a quad arrow. If I left click and drag, it moves that element around the screen. If I hover over the end of a bus, I get a dual-ended arrow, and if I left click and drag, I can expand or contract that particular bus length. He said, drop a cable on each end of this bus. So as I pick up the cable icon over here on the left tool palette, click the crosshairs on the bus, it drops down a cable for me. He said, put a plain bus, at the end of each cable. And so what he described now was the contents or the data that he had collected for his one-line diagram. He said, double click on this first cable. It's a single conductor per phase. It's a single core cable, so it's 1C. It's an outside wiring system, so it's THWN insulation. He said it's a 350 kcmil cross section, and this first cable is 50 feet long. Now the tool, once I've described this copper conductor flowing through its steel conduit, will actually calculate for me the cross-sectional ampacity and the positive sequence and zero sequence impedance, both the resistive and reactive impedance of the cable. Quite literally the most accurate impedance calculations in the industry. So now once we've accepted those values, I can right-click and copy, and then right-click and paste, and it takes all that information over to the second cable. I'm going to double-click on it to open up the dialog box. He said the second cable is exactly the same, except it's 1,000 feet long. Now we're going to go up to the transformer and double-click on it. He said, I've looked at the nameplate on the transformer. It's an oil-filled class OA, works with a fixed 65-degree rise. It's a 1,000 kVA. The impedance on the nameplate, the impedance ratio is 5.75%. May not have the X over R or zero sequence ratio, so we're going to calculate that. And then by default, it's going to plot the TCC curves when we get to coordination, and this is per ANSI standard C57.109. They said, Jim, I've talked to the utility, and I've got the data from them. They supply a available short circuit current of 45,000 amps. I take that back, 55,000 amps. The X over R is 7.6. They didn't give me the short circuit current for the single line to ground, so I'm going to use the same numbers because that's a more conservative approach. Now, the reason I like this example is because it had one protective device in the system, and it was a fuse in his utility cutout switch. So we're going to pick up the fuse icon over here on the equipment palette, put it into the utility bus right here, and then double click on it to open it up. He said, Jim, I've looked at the label on this fuse. It's an AB chance, fuse link, Model T. And now as I describe this, he said it's size 10. The tool finds it in the device library, and we're going to come here and make this a 0. And as I click calculate, it brings up a number, which means the tool has found the part number I've given it. It's been tested to an ANSI standard, and the X over R environment that the manufacturer used when it tested the fuse was 15. Now, the interrupting rating in this case is actually that of the switch, and so the manufacturer rated this at 60,000 amps, and so we're just going to put that in for that value. He said, okay, Jim, now that we've got my one-line diagram, you can change the short circuit focus, which is this lightning bolt at the top of the screen. He says, and I want to go back, and EasyPower has the ability to do both IEC and ANSI calculations. So we're going to use ANSI calculations and apply. So now that I go to short circuit focus, we're going to be looking at a half cycle balanced three-phase fault. So here at the top, I'm showing a half cycle fault, and it's balanced three-phase, and we're going to fault all the buses. It's like, now at this point, what the tool is showing me is the fault current at each of these buses. Now, we're looking at just the A phase. If I wanted to, I could look at all three phases, and that's all well and good, except with a balanced fault that's redundant. So we're just going to look at the A phase for now. What this is telling me, if bus 2 faults has a balanced three-phase fault, what's referred to as a bolted fault, each phase will see 20,625 amps, 20,625 amps per phase. If this bus faults, bus 3, we'll see 17,667 amps. Now, in this particular conversation, he was not showing any downhole loads. In reality, he'd be showing what the downhole pump motor was contributing. So I'm going to save this and make that addition to the conversation. So I'm going to put a motor downhole, which is the end of this cable, and each of these motors was 40 horsepower. So we're going to take the typical values, calculate the X over R. And so we didn't have the specific numbers on these motors, but we're taking the average values. I'm going to copy, paste the same numbers over here. Now the reason I'm doing that is that IEEE model and NFPA 70E recommends, as we do our short circuit examination, we look at contribution from both the system with and without motor contribution. So for now, we're looking at motor contribution back on the half cycle three-phase fault, faulted all the buses. And so now we see 20,625 amps supplied from the utility and 182 amps supplied from each of these motors. So that means this bus better be rated to handle 21,000 amps at a minimum. So this all looked normal. He said, okay, that looks fine. Now let's calculate instant energy. So now we utilize this Burning Man symbol, which is an arc flash, lightning bolt striking a little stick figure. And as we do that, we get new colors and new numbers. And he said, Jim, this is where I have a problem with your tools. So, okay, tell me about it. He says, well, up here where I'm working essentially on the transformer, the arc flash boundary is 27.3 inches. The incident energy is 2.4 calories per square centimeter at a working distance of 18 inches. So I know what PPE I need to wear as I work on this bus. If I walk down to this bus, the arc flash boundary is 28.3 inches. Incident energy is 2.5. 18-inch working distance, I know what PPE I need to work on here. If I walk down the road to this bus, the bus 4, my arc flash boundary is almost doubled, my incident energy is almost tripled, and now your tool's telling me I need to put on more PPE to work on this bus. What's wrong? I said, I don't get your point. He said, I've been an electrician for over 25 years, and anybody that works with electricity knows the farther away you get from the energy source, the lower the energy is going to be. And your tool is telling me that's not the case, that the energy is actually going up here. So what's wrong? Well, my response to him was, you know, I've been an electrical engineer for 25 years, and I agree with you. I don't understand how the energy could be going up at this point. Well, the significance, the bottom line, is that the next step in any study that you do when you reach this point is to let the tools show you what's going on and how the calculations are being made. And to do that, I utilize this arc flash, arrange for arc flash icon at the top, which gives me the ability now to look at both the one-line diagram and the calculations that are being made on each bus. If I look at bus 2, it's a 480 volt bus. The protective device is the fuse. Based upon the type of bus that we have defined, the bolted fault current, the arc flash gap, the space between any bare conductors, is 25 millimeters. We already knew there was 20,994 amps available at that bus. According to the IEEE model, the maximum current an arc would draw under these conditions would be 10,500 amps. According to the manufacturer's datasheet for this fuse, at 10,503 amps, that fuse will blow or clear in 68 milliseconds. So that gives us the ability to calculate the arc flash boundary and incident energy. If we go down to bus 3, same voltage, same fuse, same air gap, but now we're working with 17,987, of which IEEE says the maximum current an arc would draw under those conditions is 9,203 amps. According to the manufacturer's data sheet, that fuse will blow in 83 milliseconds when exposed to that much current. If we go to bus 4, same voltage, same fuse, same air gap, but now the maximum current that we have for a bolted fault is 4,519 amps. The maximum current an arc would draw under these conditions is 2,828, much lower than we had at either of the other 2 points. Consequently, it's going to take over 3/4 of a second for that fuse to blow. But now, and so we put all those numbers into the IEEE equation, and we show we have an arc flash boundary that's quite a bit higher and an incident energy that's quite a bit higher than the other 2 buses. So what it amounts to, if I'm wearing the same PPE as I had on when I worked on this transformer terminal, the explosion from a fault that I was working on down here would be 10 times longer than the explosion that I'd be exposed to on the transformer. So consequently, that PPE would not be near adequate for my protection. So that's what I refer to as the arc flash paradox. Now, that's it's pretty, I don't want to say trivial, but it's something that most of us, especially if we've been in the industry for a long time, have not really appreciated. And I like to bring up that point as I'm starting a discussion for beginners, because it will impact, I think it's necessary to understand that phenomena. And both the electrician and I at the same time said, I get it. Time is everything when it comes down to arc flash incident energy. So as we're calculating arc flash and collecting data, we need to keep that in mind, because the data that we're collecting has bearings in several different respects. First of all, we're calculating or developing the impedance of the system from the source to every particular load. We're looking at the contribution from each of those points to any given bus fault. And at that point, once we've determined what the fault current is, what the fault current would be if that were an arc that were creating the fault, and then finally, how long it's going to take to terminate or extinguish the arc. So all those are key factors when we're doing the coordination. Now, so as far as conducting the actual risk assessment, which is, as I mentioned earlier, just a portion of the overall compliance, we've collected the data, we've drawn a one-line diagram, and in the process, we're utilizing EasyPower tools to enter the data. This creates the digital model that allows us to do the analysis. So that's what I'm going to jump into now. And let's take a more typical example, which has distributed protective devices, which was the only real fault with the last example. So let me kind of close this out and jump into our all right, so we've collected the data, we've drawn the one line, we've entered all the information. Probably the only element that I didn't talk about were panels and MCCs. And again, I'd encourage you to either contact the EasyPower website for more videos in depth, or join us for the 4-part series in October. Once we've got our data entered, we're able to go to short circuit focus. Now, those of you that haven't used the tools, one of the nice things about EasyPower is that if I have a lack of data, let's say I had a cable out here that wasn't terminated or populated with data, I try to go to short circuit focus. It's going to say, Jim, are you sure you know what you're doing? Do you want to see an error list? And certainly I do, and it kind of points out what's going on. So I'm able to go back to my one-line diagram and undo the last step that I did. So I'm going to take that cable out. So now that I've collected the data, I've populated all the different points, drawn my one-line diagram, I have no errors, I'm ready to go to short circuit focus. First thing I want to do is to look at half cycle, 3-phase fault. Now, we haven't talked about it, but there's other types of faults that could be applied to the system, and they are important as part of a short circuit study to understand how the system will respond to a ground fault or a line-to-line fault. But for the purposes of arc flash incident energy, they're not taken into account because it's a model. The IEEE model only applies to balanced 3-phase faults at this time. So we'd fault all the buses. Again, we get nice colors, nice numbers, and these are showing us on the cable, in line with the cable, is each branch current contribution. On the oblique is the total current, fault current, which will include contributions from all sources. And since we have motors downstream, we can see that the motors during the first half cycle are contributing to the current for that fault. If we look at 5-cycle and 30-cycle numbers, so this will be the current at a 5 cycles into the fault, the one thing that's changing is the motor contribution. For small motors, at 5 cycles, the contribution is pretty much faded away. And certainly for 30-cycle motors or 30-cycle faults, all motor contributions pretty much been eliminated. Now, the next step in the process is more often than not what's referred to as coordination. So at least checking the coordination of the breakers. And what's meant by coordination, if I have a fault, a remote fault, let's say on this 10 horsepower motor, will my breaker system, my scheme that I have set up for my protective devices, will it eliminate that fault without dragging down the rest of the system? So that process is called series coordination, and in the in the vernacular of arc flash, the need to reduce incident energy actually contradicts the need for doing series coordination. Series coordination, by the definition, means I want this protective device to eliminate the fault as soon as possible. I want this protective device to be slower so that it gives the downstream breaker a chance to work, this to be slower still, and then finally the fuse to be the slowest of all, so that I don't take down the whole plant for just this remote fault. Well, EasyPower makes available this coordination module, which allows me to go in and fault the bus. Let's say fault this little bus down here by this motor. What it's showing me now, if I fault this single bus, it's showing me the fault current that's coming from the utility, 13702, the fault current coming from the motor. But if I look upstream and at these sister branches, I can see the contribution current that each one of these remote buses is making to my isolated fault. The significance of that is all of this extra current could actually be impacting and or interfering with the coordination of my plant. To that end, once I've calculated these short circuit currents for a single bus fault, the tool allows me, by invoking this little keyed item at the top, sequence of events, it shows me now if I have a fault at this bus, that this breaker will trip in 17 milliseconds, this breaker will trip in 50 milliseconds, this breaker will trip in 340 milliseconds, and finally my fuse trips in 419 milliseconds, or just under half a second. So at that point I've checked my sequence of events, and I'd want to do that across the board. The tool allows me to say, well, that's nice. How about showing me a sequence of events report? And if I come back here and fault this bus again, my little report shows up. And now I can see that I have separation between each of the buses, and it'll give me a warning when things aren't properly coordinated. Now, for the purpose of this discussion, I'm not going to get into all the details of how to do coordination, because that's a fairly in-depth topic in itself. For now, we're going to assume that we've checked the coordination. If necessary, we've done a coordination study, protective device coordination study. The next step at that point then would be to go and produce the reports. I'm going to go to the short circuit focus, look at my short circuit reports, create a high voltage and low voltage half cycle report, create an equipment duty report, and let's go ahead and expand it and make everything medium format. And it says, okay, the next time you do a bus fault or a system fault, those reports will be generated. I'm going to create a fault all the buses. The window reduces because it's created all those reports and put them at the bottom of my screen. And we can look at those in turn. We'll notice here on my equipment duty report that, and I can actually do this on the one-line diagram. In short circuit, I have an icon here that shows me equipment duty. I don't show anything flagged on the lower buses, but when I get up here to my fuse, it says I have a negative 8%. When I look at the details on that, that says, well, my fuse itself was rated for 60,000 amps. We're actually seeing 55,000 amps as a worst case. So it's within 10%, which is where I set my warning level of being non-compliant. So that's not an error at this point, it's just a warning. Whereas all the rest of my protective devices are not exceeding the worst case fault that the system will see at that point. Other reports are going to be my low voltage half cycle report. And again, it's showing me each bus, the worst case current, the X over R ratio that the tool has calculated for that part of my system, and how it's compensating on each particular device according to the manufacturer's test environment. and the tool automatically accommodates what that compensation needs to be. And so this indicates that I don't have any other errors as far as equipment duty. Another report that I'd want to show is, so we'd have the same thing for my high voltage, and then we've been looking at, this is another requisite or required report referred to as the arc flash hazard report, and it shows the calculations that are being made at each point in the system, and consequently the controls that are being placed on the calculations. And I'm just going to refer to this briefly. When I'm in short circuit focus, I have available to me short circuit options in the EasyPower tools. One of the tabs is arc flash hazard, and this controls all the applications of the model that's being used for calculations. And again, in the documents that I used under reference, the IEEE 1584 is the de facto standard model that's used for arc flash, and these are the controls that are recommended or allowed in terms of applying what that model requires. And one of those recommendations is compare 100% arcing current with 85% arcing current and use whichever is worse for the instant energy calculations. As I look at the arc flash hazard report, that comparison is being made and reflected in the color of the type in my report. When I have dark type, the tool is selected 100% arcing current as the worst case. When the type is magenta or purple colored, then it's using the 85% arcing current, which is producing a worst case instant energy. I'm happy with the results of both the short circuit, the equipment duty, the coordination report, and now my arc flash calculations. I'm ready to produce the labels. The tool has built into it a label editor, which will allow me to take the data from each of these indicated buses and apply them to a template. Again, there's 15 to 20 templates included with the tool. And if I wanted to make a modification, for instance, say I wanted to put my own logo or I wanted to change the wording, I would use the built-in label editor. And here I can add lines, rectangles, ovals, insert text, insert images. For instance, if I wanted to insert another logo or a logo for my company, I might select insert an image. The last image I played with was this warning symbol. So instead of that, I would select my logo and then position that wherever I wanted this to show up on the label, and then modify that position with these little adjustment boxes. So there we have 3 tutorials, webinars pre-recorded on the website specifically for modifying the label presentation. So once that's all done, I can scroll through each of the buses now and see how the information is being provided or demonstrated, illustrated on the label. For instance, on bus 3A, we're showing that bus 3A is a 480 volt bus. The arc flash boundary is 10 inches. The instant energy is 0.5 calories per square centimeter. Now, according to NFPA 70E, this information, 0.5 calories, is what the operator or electrician needs to refer to when he's selecting PPE to work on this bus hot. And he needs to comply with NFPA 70E table H3B. For shock boundary purposes, it's a 480 volt bus. 3 foot 6 inches is the limited approach, and 1 foot 0 inches is restricted approach. So again, all this information can be modified, and as I scroll through the buses, I can see that it pulls up that specific information for that bus, including what's the upstream feeder breaker that would be used to isolate this bus if we wanted to do so. So all of that's included in an ArcFlash report, and that's how the tools help me produce the calculations and the collateral material that would be stored or included in my report. Okay, I'm not going to have time for questions. Certainly, if you've got other questions, more than welcome to submit them. I would like to recommend that you attend the 4-part series which we are conducting next month, labeled ArcFlash the Easy Way. It's a 1 hour per week series focused on NFPA 70E compliance on the whole, not just on the calculations. The first installation is industry standards and regulations. Again, those are evolving, and it's important to stay up with those changes. And I'm not sure that we're going to have out the new edition of NFPA 70E by that time, but if we do, that will be included in that presentation. The following week, we will emphasize data collection, which elements need to have data collected, and basically the priority of each of those categories. Then the third week, we will go into much more in-depth analysis and how the tools will allow you to accommodate all the variables that can affect the IEEE calculations. Then on the 24th, we will be getting into all the labels and reports and how to utilize the tools for an ongoing method of maintaining compliance and improving employee safety. So I encourage you to register on EasyPower.com on the webinars page. Thank you very much for attending. By all means, stay abreast of new presentation material and new webinars. And as I say, if you have questions, I'd be more than happy to answer. Submit them to me via email, jim@easypower.com, and we'll talk to you next week.